Hi Audrey, it's Martin, and this is the 15-minute presentation for the Sony Interactive Commercial Staircase Design. So moving swiftly on, looking at the context, I just wanted to put a page in here just really to tie everything back to the original design for the Sony interior, because it's important to understand, I think, the shop layout and the overall look that we're trying to create, which was obviously this very modern sort of high-tech image. Now, on the research, I don't have time within a 15-minute presentation to go into detail, so I'll just highlight the main criteria that affected the design. So starting off with the eco-friendly ideas, the main thing that came out of this research was the fact that I wanted the materials chosen for this to be infinitely recyclable, which I think was an important criteria. So based on that, I looked at aluminium and titanium alloy and recycled glass. So recycled glass is a very flexible material from a design point of view. Aluminium and titanium alloy was originally developed for the aerospace industry. It has got a very high-tech finish to it with a sort of polished steel. It's very lightweight, but it's very strong. So it's sort of ideal for what I wanted. And both materials are infinitely recyclable. So they do go with the eco principles. The other thing I wanted to look at was the actual process. While I was doing the research, I discovered that there was a new 3D printer being developed in Europe for much larger scale. At the moment, 3D printing is still thought of as very sort of small scale. This deals with very large industrial components. So I could have whole components of a staircase 3D manufactured. And it was important to understand this process because as I was designing it, I was constantly thinking, well, how could you actually print this? How would the machine work? How would it operate? So it did influence the design. I also did research on 3 different staircases, mainly so that I could analyse them and to see what I could learn and take forward into my design. So there was the Alvar Aalto staircase, the Mies van der Rohe staircase, and the Foster and Partner staircase at Apple in New York. So starting with the Aalto staircase, it was a fascinating staircase, obviously a design icon. Quite a lot of lessons to be learnt from this, specifically the fact that these treads appeared to float because they had the steel rods, steel directly behind the treads supporting it. And then when I looked at that in more detail, you begin to see, well, how did this go together? What materials were used? So it was a fascinating staircase in its own right. I went through the same process with the Mies van der Rohe staircase. And I chose the Foster and Partner staircase specifically because it was within a high-tech environment for a high-tech company, and it reflected all of those aspects. So I think it was particularly relevant to what I was doing. Now, as you see, this is a spiral staircase coming around a central column, and it's all done in polished steel and glass. When you look into the detail, you'll see that the treads appear to float, but they're actually cantilevered. And when you zoom into the treads on this bottom image here, you can see the detail that they've gone into, which is absolutely beautiful with these lovely polished edges, the way it ties into the glass, even the tread detail to give you grip. It's a beautiful thing. And there were lots of elements on this that I wanted to bring into my own design. Now, when I looked at all 3 staircases together, the one thing that occurred to me was that they were all supported in different ways. When you look at the top right-hand staircase, the Aalto staircase, it's supported off these 3 steels at the back. Then you move to the Van der Rohe staircase, which is a solid steel construction braced into the walls on left and right, so a very sort of industrial approach. And the Foster and Partners staircase, a very, very elegant, simple approach where it was actually cantilevered, so they're using, state-of-the-art engineering to actually create that support, which I liked. The other thing that occurred to me was that all the staircases that I've just mentioned, they were all concentrated on stiffening the staircase up. And if you look at, for instance, the sports industry, where you're playing sports, they actually spring the floors to absorb the impact. So I thought, well, why shouldn't a staircase do that? It's very counterproductive to stiffen it so that all that energy comes back up through the joints. So I did these little sketches on the left-hand side. That then led to the idea of, well, if we can do that, why not use that energy? So if we look at that, you can see how that downward energy on the step could actually form that rotary motion. So at that point, I thought, well, we could actually put some kind of a very small amount of flex into the staircase, which absorbs the energy, takes the weight off the joints, but also turns potential energy into kinetic energy. At that point, I'm thinking, great, I'm a genius. And then, of course, you discover you're not at all, that somebody's already thought about it. I found this company called Pathogen. So you see the images on the right-hand side. They're developing a pavement system with these micro generators underneath. So the footfall creates a minor depression, which then generates energy. So I suppose the bad news is I'm not a genius. The good news is the technology is actually there to do what I want to do. So it's all good. So going through then into design development, these are the original sketches that I did. I mean, the core principle of this is that I wanted to form a modular system that could be repeated. So yes, it's been done for the Sony environment, but it could be done for anywhere in modules. So I designed a simple track for the wall. The treads and the balustrades would be 3D printed in one complete section and slotted into the track. So these would adjust in height. Now, the way I'm looking at designing it at the moment is that these will be manually adjusted to the heights that we want. There's no reason, if we did further development on this, why this couldn't be motorized. So all the treads could be lined up horizontally. You press a button, the computer would automatically work out the floor to floor and then adjust every step down exactly where you wanted them. So the principles of a modern high-tech staircase are here. From the sketches, I went into some very basic 3D modeling. So it's starting to pull together and the ideas are beginning to work. The issue I have with these drawings is that they don't really reflect the concept that we developed for Sony. So you see in the middle that we've got this sort of graphic that I wanted to introduce into the balustrade. So that was the graphic, and that graphic appears all over the shop, and I wanted it to be a main feature within the staircase itself. So I developed these very simple 3D graphics here, showing the graphic into the side panels so that we have that very definite sort of tie-in with the concept. So moving forward to the technical drawings, I cut down the number of technical drawings I did this time because I realised on previous projects I have gone over the top with the sheer number of drawings. So I've brought this down to a level where I've just concentrated on what are the important factors, what needs to be designed. So starting with the first drawing, possibly the most boring drawing in the pack, but the most important, because this covers all of the regulatory aspects. So, for instance, it shows the height of the handrail, the fact the handrail's got to be consistent. It divides that 3.9 floor to floor up to give me the number of treads. I've isolated the fact because of the number of treads that we need a landing halfway down. The pitch on these staircases works out to 33 degrees, which fits in with the regulations. So this is an important criteria. So everything that I design going forward has to come back to this drawing and has to comply. So that's the plan I did, and it works out, the overall length of the staircase works out to 7.8, and the overall width works out to 1824. So it's quite a lot to cantilever that. Looking at the elevation, you can see it going down there. You can see the tracks on the back wall and also the landing halfway down. And then I've cut a section through that, so it's the same information, but it just starts to show the brackets underneath, and it shows the handrail clearly. So that is a continuous handrail running down. Looking from the end elevation, it begins to highlight now how frosted glass is being used to actually cover the riser so that we don't end up with any gaps in that. So again, it complies to building regulations. And the section on the right shows the cantilevered bracket. What I wanted to then do was to do more detail on that. So excuse me, this shows the bracket in more detail. It shows the main load points. It shows where there would be potential deflection within it, and it also shows the positions of the handrails as well. So this raises questions, for instance, like how are the handrails fixed? So I went into more detail again to see how the handrails would be located, how they would be fixed. What this drawing also did, because it was at such a large scale, I began to consider, well, if that material for the side balustrades is 30mm wide, and we're actually doing a 3D printing process, then why don't we do a honeycomb section inside that? And that way it would retain the strength within the material, but it would reduce the weight even more. So you've got a titanium aluminium alloy, which is lightweight and strong anyway, with a honeycomb engineered center. So you've got a very lightweight, very, very strong construction, which in turn takes the load off the cantilever, which reduces the deflection within it. I started to look at the treads in more detail. This was shamelessly stolen from the Apple store from Foster and Partners, using this sort of geometric grid. And of course, the nosings on the right-hand drawing show the raised nosings, which make it comply to building regulations. It was pointed out to me that whilst there was little or no movement on the stairs, there was a very slight spring to each step, a fraction of a millimetre, but it would be an unusual experience. So at the top and the bottom of the stairs, I've designed these studs, so for the visually impaired, they will immediately know that they're about to go onto a staircase, and there's no reason why these couldn't actually be connected to a visual or even an audible signal to warn you that you're about to go on the stairs, similar to an escalator, for argument's sake. So you've just got this safety feature built in. Again, going into detail, this idea of converting potential to kinetic energy, I wanted to do a section through the stair showing how that sort of micro generator would work, how we could actually spring it, and the little picture top right hand just shows that sort of honeycomb section that a 3D printer could achieve. And the next one, again, just showing it from a different angle, a different sort of detail. And then the final drawing shows the slide, which is, if you like, the key to the staircase, because this slide slots into the track and allows you to adjust every tread to the exact height you want. So if we were to apply this to another site and it had a different floor to floor, this would just slide the steps into the different positions for you. And then on the finishes schedule, basically we've only got two finishes here, which is the titanium aluminium alloy and the glass, but I've numbered each component and put the pictures on the right hand side just so it's a clear breakdown as to what we're actually going to manufacture. Now we get to the fun bit, the renders. So I started off with white renders in digital modeling to actually understand how it looked within the space and how it worked. I did a color digital render and a quick walkthrough. So if I just press this should play for you. So as you look at the top of the staircase, you've got a glass balustrade on the right hand side. Then as you come down the staircase, you'll notice that there's a continuous handrail running on both sides, which is important for the regulations because of the width of the staircase. Now this next part of the film, I left this in because it shows context. By showing the rest of the interior, you begin to appreciate why the staircase has been designed in the way that it has. The motif that we talked about earlier, you can see it in the ceiling, you can see it into the walls, and then of course into the side of the staircase itself. So it just gives the whole staircase a little bit of context. You can see coming round here the motif on the side of the balustrades in a little bit more detail, and the tracks on the back wall. And then as we pan around, what I was interested in is that most staircases, you don't really see much attention to detail on the underside of the staircase, whereas on this I wanted to really make a feature of the engineering. So these brackets are pieces of engineering in their own right. Then as we come back, you begin to see again the handrail and the tracks, and just as the camera swings around, I wanted to show you the riser. Now the riser could be done in either clear or in frosted glass. Just for the purpose of the visual, I've shown it in a clear glass so that you can actually see the brackets underneath. So I'm going to cut that short because we're short of time. So the next slide looks at the 3D printing. This is the actual 3D printing for the physical model that I did, and this was a hell of a learning curve for me. You can see that the printed process is illustrated on the right hand side, where it actually prints in layers. And then the issue I had was that it was printing vertically rather than horizontally. So you see the image on the bottom left hand side, it's left a very poor detail. So what I had to do was to effectively redo it so that it printed horizontally. And the bottom right image shows clearly that it's actually given me a lot more detail to the printing process, and it's a lot sharper. This just shows the construction. of all the various parts at the top. Yes, I'm using my feet to cut some of that tubing, which isn't exactly health and safety. And I'm also using a light box to do some of the glass balustrades and the glass floor. And then we come through here. This is the actual physical model that I did. I did the first floor removable, so that as we come through, I could remove the floor so that you can get a better picture of the staircase. On the left hand without the flooring in, on the right hand with the flooring in, showing the glass floor detail. Two more images. I think they're actually quite close to the digital model, these, so I was quite pleased with it. And then final image here. And then just to round off, the costings were amusing, to say the least. We're looking at almost £350,000, including VAT. I mean, I've put a provisional sum in here for contingency of 30% because it was a completely experimental thing. So there's £50,000 worth of contingency in there. But what did occur to me was that if this is repeated in the future, because of the 3D printing process I'm doing, we could do this on a mass production basis, so it could be fully automated. So on the one hand, we could fully automate it and reduce the cost significantly. I think we could reduce the cost easily by 50%. And if we followed the line of the car companies and actually looked at the way it's marketed, and we added, for instance, different materials to this staircase, and we could actually add value to it. So we reduce production costs, add value to it, and we can increase profit margins. So just to finish, that was a quick visual I did of the staircase, adding different finishes using leather and using wood if we wanted to produce it for other applications. So that's it. I hope you've enjoyed the presentation. I'm just over a minute over, so I do apologise. But I will speak to you soon. Thank you for listening. Bye-bye.